Hello, and thanks for coming. I'm faced with a very challenging task of explaining or talking to people who know on probably more than me on many of the topics that I want to cover. And so I will present the story of a magnanimous Magnon. And so trying to connect to several key discussions and developments that I think happened in our new spin on quantum magnets program, and hopefully generating more discussions and questions. So please ask questions as I go. And I would like to begin with a story which I like very much, and which, maybe at the end of the day, if you remember that story, it's will connect to some of the things you'll see later. And I have to say also, okay, so just to add once again that many of the developments that I will be describing have been done in these walls of this building and by people associated with KITP, and who it's great for me to try to convey a little bit of the excitement in quantum magnetism. So my story, okay, begins in 1941 when Pomeranchuk writes a paper in KITP on thermal conductivity of paramagnetic dielectrics. Okay? And paramagnetic dielectrics is what we now routinely call antiferromagnets. And at the time, by that time already Louis Niel in France has proposed his famous Niel state for antiferromagnet, and was developing it, but Landau have arrived at the conclusion that this state cannot be a state of quantum Hamiltonian, will not survive fluctuations in some way, and asked Pomeranchuk to look into this question. And in his paper, Pomeranchuk describes in the introduction very beautifully how magnetic moments talk to each other, and that disturbances of the magnetic configuration propagate through the crystal, and he suggests to call those disturbances Magnon. And that's the first paper, as far as I know, where the term Magnon as a essentially quasi-particle appeared in the literature. And then he says, available existing experiments suggest that magnons obey Fermi-Dirac statistics. And there is a reference to the experiment, and it's a reference to a laboratory report from Leiden, from Kamerlingh Onnes lab, from 1914. Okay. And it's possible to dig out that report, and it addresses susceptibility, low temperature measurements of magnetic susceptibility of solid oxygen. And the main finding from that report is that in the temperature interval considered, which was of the order of 50 K, susceptibility is constant. Okay? And so that's the experimental evidence Pomeranchuk had. And then he makes this dramatic assumption that magnons are neutral fermions, and constant susceptibility is explained by its Pauli susceptibility of a neutral Fermi gas. And so the first Magnon was fermion. And he then goes on to consider thermal conductivity of magnons, which are fermions, interacting with phonons, and considers different regimes where, depending on Fermi energy, essentially, and Debye temperature, different regimes are available. And it's a pretty detailed, extensive paper. And the last remark that I want to add here is that it turns out that solid oxygen that Camerlin Connes was investigating realizes spin-1 triangular antiferromagnet at that temperatures regime where that's how we understand this currently. And then, okay, you all pretty much know what happened, that in about 1949, or about that time, neutron diffraction experiments have become available, and Schul and Smart have measured neutron Bragg peak of an antiferromagnet manganese oxide, and so observed diffraction of magnetic peak that appears at below critical temperature, and therefore these experiments have confirmed experimentally the stability and the existence of Niel state. It's not. So spin 1, it's a spin of the molecule which makes solid. It's not an excitation. Excitations, as we think of them, as we understand them now, are bosons. So the suggestion of that they are fermions followed from the fact that susceptibility as a function of temperature is constant at low temperatures, which is unusual. Okay, it's not, we understand this, it's not very unusual for Niel state. You apply field and spin slightly, turn along the direction of the field, and that gives constant susceptibility, but back in the day, it was strange. Okay. And so, that's the story. And what is remarkable is that, I find, three themes that will follow through my talk emerge from that story. So first, that, excitations, elementary excitations of antiferromagnet can have exotic statistics, right? Fermions are still very unusual, even though that's what we would like elementary excitations to be in frustrated magnets. Secondly, the fact that this thing is triangular means so we have frustrated geometry, or how we understand it more now, competing interactions. That's maybe not only due to the geometry, competing interactions which lead to something basically different from simple ferromagnet. And then, very interesting now, is that it's a thermal transport that is used to investigate antiferromagnets. Okay? And so we now move to our current day. And so we are in our program and elsewhere looking for quantum spin liquids as a ground state of many body Hamiltonians, usually written in terms of localized spins. And so just to set the stage, so QSL, quantum spin liquid, is a ground state of entangled quantum ground state of many spin systems that preserve symmetries of the Hamiltonian. So these systems are characterized by fractionalized excitations, which we call spinons, and emergent gauge field fluctuations. So spinons exchange gauge field fluctuations. That's how mediated, which mediate interactions. And importantly, also the gauge fields can have their own excitations or defects called monopoles. So from 40s, huge experimental progress has been made. And in our program, we have had a number of discussions. And in one of those very nice discussions, Martin Morigal has presented to us with extensive list of interesting quantum materials realized in triangular and Kagoma geometries and spin-half magnets, and it's roughly about 20 of them currently in the consideration. More, and some of the most interesting I write here, and they were talked by, about cesium, ytterbium, selenide, and at the conference last week, and then there is this new material about which I come back to in a few minutes, put in perspective. And theoretically, it turned out, after many years of extensive research and investigating many various models, that triangular lattice antiferromagnet, again, but for spin-half Heisenberg model, so when spins interacting by exchange interaction, on triangular lattice with interaction between nearest neighbor and next nearest neighbor. So J1, J2. J1 is so white lines on this drawing, and some of the J2s are just orange lines, so connecting spins at slightly longer distance, next nearest neighbors. So both J1 and J2 are positive, that is antiferromagnetic. And this system has been studied extensively, numerically, mostly with DMRG, but also other techniques. And what emerged is that as a ratio of J2 to J1, this simple-looking Hamiltonian has the following ground states. So for some J2 to J1 ratio of order 700s, it's a 120-degree structure where spins form, on elementary triangle form this famous 120-degree structure typical of triangular antiferromagnet. For bigger values of J2 to J1, it's actually a collinear state, which is called stripe. And then in between, there is a disordered quantum state. And nature of which is still debated, but I want to today present or describe to you emerging kind of evidence that this may realize a Dirac quantum spin liquid state. Okay? And so many people worked and are continuing working on this problem, and it's impossible for me to give credit to all, but there are quite a number of people who passed or participated in our program, and I try to mention them. So let me now lead you to kind of the logic, give you a idea of how this can be the case. So we start by writing Abrikosov fermion parameterization for localized spin 1/2. So written in terms of fermions C on site I and alpha beta spin indices. You plug that parameterization in your Heisenberg Hamiltonian, and of course end up with fully interacting Hamiltonian involving 4 fermion operators. But we proceed bravely by investigating one of many possible mean field solutions, and the one which is relevant for the story, so is written in terms of fields chi, which live on the links of the lattice. Ij are spatial indices, so they live on white and these orange bonds. And this chi has a magnitude and phase. And the interesting solution that we are looking for has constant magnitude, and the phase, which I will write as exponential involving some capital Aij and little aij. And so capital Aij is a C number stationary kind of phase, which is adjusted to this so-called staggered pattern. So on triangular lattice, sum of Ij's on the links belonging to up-pointing, say, triangles, that sum is pi. Whereas on down-pointing triangles, that sum is 0. It's possible to choose phases in this way. So to have a solution, to have such a parameterization, such a distribution of fluxes in the ground state, and this requires, two-side unit cell. Okay. So leaving little aij's aside for a moment, so we have non-interacting fermions moving in such flux background. This problem can be solved, and one finds that there are 2 Dirac nodes located in the Brillouin zone connected by time reversal symmetry. And, okay, so 2 Dirac nodes. So these are Dirac fermions. And then we come back to investigate fluctuating quantum field denoted by little aij here. And so it's a dynamical and compact field. Compact means being a phase of a link variable, it lives, is defined from 0 to 2 pi. Okay? And so zooming in, so from this Hamiltonian expanding in fluctuations of aij and zooming in on the regions around Dirac points, one obtains famous and beautiful, I want to write Lagrangian, Dirac Lagrangian, which describes 2 nodes, maybe I denote them by J, 2 nodes. The fermions psi bar and psi are So psi's are two-component Dirac spinors. They're two-component because there are two sides in unit cell. And A is dynamical quantum field, which is compact. And so that's how theoretically, the steps leading to the Dirac model. Yes. So it's a linear superposition, which, like in graphene, you diagonalize the Hamiltonian, and you find some. Okay. Okay.
S is being written as quadratic in C's.
Yes.
Now you have quadratic Hamiltonian. Why isn't it quartered?
Right. So that's because I put an arrow here.
Yeah.
It's a mean field approximation. So I'm introducing an ansatz. So at this point, it's basically a guess. Okay. So this type of studies have been done for a long time, and so this solution emerged as a very competitive in energy. So if you calculate ground state energy of such solutions, with that particular staggered pattern of fluxes, it's lower in energy than other configurations. Okay. So, but it is an approximation, of course. Yes.
The Dirac points that you mentioned,
yes.
Are they guaranteed by some symmetry,
or
is it an artifact of an approximation?
No, they're guaranteed by this structure, flux structure.
Could you elaborate?
So okay. So there are time reversal and discrete symmetries of the lattice, C3. So which, so why, okay, just like you're asking. Well, you can have infinitely many, flux structures, and you can compare the energies. So I mean, okay. So already.
So is it an artifact of your mean field approximation, or any state that you would faithfully solve would produce such?
No. So when you say any state, so again, so it's a consequence of flux. So it's a state that minimizes energy, and it's the existence of Dirac knots is tied to these pi's and zeros. Okay, so they're not. So if I take a different, if I remove pi's, I'll get very different state. So now so it's a symmetry. So the fermions. Okay, so symmetry of fermions is okay. So it's okay. So so the fact that this maybe this ansatz forces the two sublattice or two side unit cells, and so so you have just like in graphene, you have two Pauli matrices, you have Hamiltonian 2 by 2. And it involves two Pauli matrices, and so so again, time reversal precludes sigma 3 appearing, and that's basically probably not getting, but that's the reason for the knots, the particle hole symmetry, and the knots appearing in this problem. Yes. If I. Yes.
For the Dirac equation to work with, is the A index
A, sorry.
Because
So-
the
so-
cluster index is contracted, but A is, the mu is just dangling there.
There are, yeah, okay, so the parentheses are put wrongly. Gamma mu is outside. Yeah, thank you. It's, yeah. So that part is, yeah. Okay, so let me, okay, continue. With, right, so, okay, so that's, okay, so we arrive at that, okay, so we arrive at this, okay, so at this point, okay, once again, aside from, numerical calculation of saddle of energies in this particular mean field ansatz that is proposed, we are, okay, it's a good candidate, but okay, so for possible state and considering fluctuations about the proposed mean field, we arrived at this Dirac equation, Lagrangian, and we can investigate properties of this thing, of course, analytically, but the big question remains essentially, how good is this guess? And that's a big question, because energy alone, well, okay, I guess if we could compare all possible states, energies of all possible states exactly, then that's one way to think about it. But people have done extensive numerical studies of spin models, right? So the question is, so there is a theoretical question, what can we do to convince ourselves that the disordered quantum spin state observed for this in that range of parameters of J2 to J1 is indeed describing Dirac fermions coupled to gauge fields. And this is where, okay, I want to go. So very recently, several papers, and in particular, paper by Wittek, Caponi, and Leuschli has appeared, which addresses this question in an interesting way, which I want to try to quickly explain to you. So they studying J1, J2 models that I already introduced exactly on a 36-site cluster. So it's exact diagonalization.
Oleg?
Yes.
So in that throughout field theory, the little a has a natural.
Yeah. So it will, yes, if you, yeah, it will be generated, right? So yes, it's a dynamic. So there is E squared F mu squared. Okay. So they study this, okay, on 36 site cluster, okay, and identify the, sorry, just a sec. Identify, levels and the quantum numbers, that is spin, momentum, and how these different states transform under lattice symmetries that they have in their cluster. So it's extensive exact analysis, but very sufficiently small system, even though that represents state-of-the-art for modern numerical calculations. And then, so the crucial step that they take a next step and compare it with QED3 as described here on the same cluster. Okay, which means that they put, so essentially this fermions on the lattice, which is the same lattice that on which spins live, and so it's a half field, so lattice for fermions. And then consider or calculate numerically all possible excitations or quantum levels, and so they know, that is, they have exact wave functions for spin model, and then they work to construct wave functions and their excitations, ground state and excited states of the lattice model of QED3, which is defined as I sketched here. So there are two Dirac, so it's a lattice spectrum, but at lower energies, there are two Dirac nodes. You fill fermions to lowest band, and then you construct excitations, which are several kinds. So one you can just consider usual particle Hall excitations, kind of transitions promoting given fermion to a different state, and this can be within a given valley or between different valleys, right? And so in this way, so these are you kind of construct various possible fermion bilinears and their wave functions, right? In addition, and very importantly, so as I already said, the gauge field little a is compact, and so in addition to having kind of continuous fluctuations, it has defects which are monopoles, which are sources when a flux changes by 2 pi, it serves as a magnetic charge for this field little a. Okay? And sorry? Sorry, I didn't hear that. No. So this is, so I'm talking about instant-on events. So if you write partition function, for example, right? So your A flux through through your system can change by 2 pi, and then this will be a source for.
It's still associated because say some spin system, and then you have interaction with this gauge field, right? And then the strength of the interaction is given by G factor, right? Like for Dirac fermion, it's like G factor equal 2. And here it could be n of this, right? Or something.
So here charges in the way I've written is 1, right?
Electric charges. So I mean, charges.
So at this point, okay. So A is a gauge field. So okay. So it's in 2 plus 1. Sorry.
There's interaction with the charge, and there's interaction with the spin for vector field. And interaction with the charge is electric charge, and the
Sure.
with the spin is given by G factor.
So my spin sits, so it's index S here, right? And this thing is diagonal in S. So I'm at this point I'm describing excitations of gauge field, right? Okay. And there will be, since it comes from the lattice, there are these, that's where compactness shows up. And so we can construct these excitations. So, the monopole, okay. In the for solving, let me describe and then maybe flux, 2 pi flux, okay. So of the field A. So for that, so on that given lattice that they consider, okay, which I'm extremely schematically, sketching here, you pass flux to pi, which means calculationally you distribute additional flux on top of capital A's, which I already described here, such that you have 2 pi passing through the full lattice, and you recalculate energy levels, and you find that this 2 pi flux leads to appearance, so this monopole leads to appearance of 0 Landau levels. There are 2, or, okay, maybe it's, I better say, so there are, okay, two 0 energy levels, each from the valley, which you then populate with fermions, okay? And that represents a monopole which couples to, okay, is magnetic charge for A, and it interacts with our Dirac fermions via these 0 energy levels, okay? And the point of all this, and I need to speed up because I'm afraid of not getting to my point, so that this is done numerically on the lattice, okay? So, and then they consider overlaps between wave functions of the spin model, so which I denote by, so obtained in exact diagonalization, and wave functions of various bilinear or various excitations of very different states obtained in this so defined QED. Okay, and these are 2 different, right? As I try to describe, these are 2 different things, and they calculate these overlaps, and they find very schematically. So if one plots an overlap, so in the region of interest, and this, okay, maybe I should add that so constructed states involve more than 100 states, close to 200 different levels. They calculate overlaps and find that these overlaps are finite range between 0.5 and 0.9, depending on type of excitation. Okay, and so this is very unusual, right? Because this tells you that this Dirac equation on the lattice, as I described, and spin model in a given range of parameters, and so, this is a very schematic picture, but the overlaps pick up in that intermediate region. Yes?
So for the QD3 states, do they have to do a projection?
They do, yes, exactly. Thank you for yes. So they do, yes, Gutzwiller projection, right? So that these wave functions correspond to 1 fermion per site. Yes, I forgot to, yeah, it's an important step, yes. Okay. And so, okay, so this is new. Yes.
The overlap of 0.9, is that regarded as a large overlap or a small overlap?
It's finite overlap. So for one, right, so maybe, right, so the fact that, so it's not just some one thing that, so that one particular state that overlaps well, reasonably well, with some other state, right? It's an extensive set of levels on ED side and on QED side, which have finite overlaps. That's basically a statement. So that it looks, it's a systematic trend, not a random feature of two unrelated wave functions. Sure, there are strong finite size, but point here is that it's both calculated on the same lattice, right?
Presumably the overlap will go exponentially to zero.
If you, yes, but on a finite, okay, given what is possible, it's finite, and so okay. In my view, it's a strong indication of that this intermediate state may indeed realize Dirac spin liquid. It's not a proof, but it's something new which goes beyond order parameter, energies. It's identification of quantum numbers. Yes?
Does a QED normalization include OG1?
No.
So I have a question on
Yes.
Christian's comment. So Christian, what you're saying is that if you run out the infinite system, you expect this overlap to be small and small and small and zero, right? Is this a statement that you can make rigorous?
It's always true.
It's
It's always true. Okay, that's what I want.
I.
So you
Because
if you go
Hilbert
to
space is too
infinity,
big.
if you go to
You'll be.
state is not anymore.
Well, what you should specify is there's no tuning parameters in the variation laws.
No, it's very
zero.
nice, but it tells us
Not
that
even
it's-
1 for J2 over J1.
No, it's very good, but it's for a finite system. So
Of course.
it's
Sure, no, but
it's
that's.
the physics of a finite system. That's
But okay, so physics of finite system. Okay, yes.
yes. No,
So,
it's very nice.
so with what one does, one constructs. Okay, so on ED side again, one knows quantum numbers. On the other side, one constructs excitations, for example, with those quantum numbers. Given momentum, spin, transformation under discrete symmetries, right? And so the again extensive overlap of many levels suggests that there is this description is behind that. So, am I out of time? Oh, okay. Huh? Okay, because so sorry for So what? Okay, maybe. So maybe in words without.
On the QD3 side, what that diagram, that comparison, what's the value of the charge? Is that adjusted or not?
The value of the. No. So on this side, so again, so one does lattice, right? And in that lattice, so what I raised, so there are phases of your chi ij, right? Okay, and then so there is a mean field phase which gives you this pi flux, and then you.
There's no fluctuating gauge field.
No, so okay, so it's a QED3 in restricted sense, so that you construct what you think should look like QED3 by, so for example, for monopoles, again, you add additional flux to push additional flux through your lattice, recalculate all levels, populate them so that to maintain particle hole symmetry, so fill the, okay, and that's how you construct, this thing, right? And, okay, and they happen to have an overlap, good overlap with, again, corresponding levels in exact diagonalization, and that corresponding is identified by the quantum numbers, momenta, and again, as a discrete irreducible representations, right? And so that's a point. So QED3 is not full lattice QED simulation with dynamic field, right? Okay, what I want to, okay, so I have no time to draw, but I wanted to add to this, so there is, okay, more to my story, and namely that's the remaining theme which I have not touched with thermal transport as initiated long ago by Pomeranchuk. And here the focus is on both experiment and theoretical developments for the thermal Hall effect, which has become a very interesting, intriguing, and complicated experimental probe, and for which we have several theoretical descriptions which range from something familiar to many kind of analogous to Hall effect in electron systems with non-trivial band topology. And so there are cases, both theoretical and experimental materials, which seem to realize kind of ferromagnets with perturbed by Dzheloshinsky-Marie interaction in such a way that resulting excitations, magnons, which are bosons, nonetheless have non-trivial band topology with finite Chern numbers, with non-zero Chern numbers, and that is responsible for can be explain some of the thermal Hall observations in those kind of materials. But there is a second class of material of experimental puzzles, much more not well understood, where the thermal Hall seems to be strongly dominated by phonons, and the question emerges, how phonons or magnons for that, and so which are not which are charge neutral excitations in the sense of usual electric charge. What is the source of Lorentz force for them? And this is an ongoing theoretical investigations where emergent picture, a lot of which has to do with works of Leo Mangioli, Lucille Savary, and Leon Balens here, is that phonons learn about time reversal breaking from the spin system, from spins with which they interact. Okay, the spins themselves are overwhelmed by essentially phonon transport, but they serve a very important role of having kind of passing on time reversal breaking information, so to say, to phonons. And this is a very interesting and promising direction, but I would like to conclude by saying so that, we kind of made not a circle, but somewhat of a spiraling progress, where the themes of fractionalized excitations emerging as a result of competition between localized magnetic, between localized spins, and thermal transport investigations of these have become, again, very strong and active research field in our field. And so the Magnanimous Magnon keeps delivering good things to us. Thank you.
Since you mentioned right at the start.
Sorry, I was told, I forgot, I should pass that.
Just very simple. Since you mentioned at the start, in principle, there are many, many ways how you can put the mean field parameters.
Yes.
And so I'm pretty impressed by the large overlap. So the question is just, you might venture to look at a different state.
Sure.
And did the authors of that paper, just to get a feeling, if you take one potential other candidate, check on the overlap with the ED, just to get a feeling, goes the number down from 0.5 to 0.001?
Okay, so in that particular paper, they don't.
But shouldn't that be done?
You
taking
can suggest
different.
it to them, sure.
Okay.
I mean, so the list, of all possible. So
No,
So what we know, again, and thanks for many, papers who worked and continue working on this. So and energetics of this state is good. So that's, of course, isn't very important, right? It's and so I also maybe so similar analysis is in progress, as far as I understand from Federica, on Kagome lattice, and there are strong indications again of Dirac spin liquid emerging in Kagome. Okay, and so whether or not, so it would be interesting, I agree, to look on something like Z2 spin liquid state and calculate overlaps. I don't know of such, but
I'm not questioning the type of state that might be preferential. I'm just trying to get a feeling of what the overlap would be. Yeah, if the state wouldn't be the preferential one, that's just to get a feeling, It's not, okay, anyway.
So it's interesting, but I cannot, point you off the top of my head to anything of.
Oleg, maybe you've said this, but do I understand correctly that the state that you drew sort of also involves some symmetry, some real symmetry breaking? So you need to decide whether the up-pointing triangles have the pi flux or the down.
So for fermions, yes, right, but it's it's a projective representation, right? So we are doing this PSG, so it's, right. So the mean field breaks. So for fermions, the unit cell is two sides, as I mentioned.
Yeah.
But spin Hamiltonian has all the symmetries of the triangular lattice.
So it seems to me like if you do a C6 rotation, you can't go back by a gauge information. So that symmetry is truly broken. Is that not
so
true?
you have to do some of the lattice symmetries are supplemented with SU2 rotations, of the bigger group. So what I'm trying to say is that it's not unusual, right, that the mean field breaks written in terms of partons breaks appears to break the symmetry, but all the physical observables preserve them.
On the energetics, just intuitively it seems that a gapped state would have better energy.
Gapped, you said?
Gapped state. So if you play with fluxes, for example, if you make the number of zeros not equal to the number of pi's, would this open
then
a gap?
You break time reversal, right?
Right.
Of some sort. But so the question, if you're asking, so Dirac is more difficult to gap than other states, right? So you need, but in general, again, it's one. So if the question is why is this particular state, right, and not
some gap state which would have lower energy.
So you can, this what I described is it's a construction of U1 spin liquid, right? One can gap down to Z2, and people have done that. I guess the emergent for that particular model. So there are still some suggestions in the literature that the state, what's happening in between this intermediate region can be something else, but it's a very strong contender. I cannot say provide more intuition than that, I think.
I would just comment in response to that question. I mean, what Oleg was saying about comparing different states, as he said, has not been done for the full spectrum like this, but there's been really a lot of work comparing different ground state wave functions, in particular Federico Becca, I'm not sure if he's here, he's looked very hard for instabilities of this Dirac state, with lots of perturbations, and even though you might think a gap would open up, it really doesn't. they always find that as they, make they do a lot more work to improve the wave function, and the gap always appears to, you should speak, but as far as
Yes.
And there are few possibilities, different symmetries, and according to our calculations, the U1 is always stable, at least on a finite system, let's say. But if you do thermodynamic extrapolations and so on, the evidence is quite clear that this is the best, at least in the family that you can construct within this approach.
Okay, one last.
So it's related to the question of the gap. So QED3, my understanding is that we don't even know if it's gapped or gapless, right? At large NF it's gapless, at 0 NF it's gapped. So here is the kind of point of the results you presented to tie the fate of this potential spin liquid to QED3 without saying whether or not, either is gapped or gapless. Is that okay?
Yes.
Thank you.
So, I mean, the jury is, yes, we don't know what the critical N is for monopoles relevant.